Welcome to this video on damped harmonic motion. So far we've been looking at something called simple harmonic motion, and it looks like this. You pull an object away, you let it go, and it continues to oscillate back and forth, like this. So what makes this simple? Here's the answer. This system has no friction, and for that reason, the total energy is always going to stay the same. It moves back and forth. The total energy is constantly converted or continuously converted rather, from kinetic energy to potential energy and back and forth. But what if we introduce some friction to the system? Let's stop this thing here, slow it down. What if we consider a system that has some friction? So take a look at this. I put in a little friction, I pull it back from the center position, I let it go, and as it continues, as it bounces, in successive bounces, it's not going as far down as it did before. So the energy is going down, and we can clearly see that because those oscillations get smaller and smaller. Now, that was a pretty heavy case of friction. It doesn't always have to be that heavy, the friction. We could imagine that instead there was some light amount of friction, some light damping, so that the oscillations, so here's how far down it's going, is where my mouse is, and as time goes by, it goes less and less far, but it takes a while for that reduction to occur. So there's less reduction with each oscillation. But it's clearly going less far than it did at the beginning. That we would call light damping. So a system which is oscillating with simple harmonic motion or even damped harmonic motion has its energy given by this equation. So the energy is a function of the amplitude. In other words, if the amplitude decreases, so does the energy. We could say, in fact, that the total energy is proportional to the amplitude squared. That'll be useful in a little bit. We've said that some oscillating systems experience damping. What is damping? It's the friction of oscillating systems. But here's your official IB definition. Damping is the opposition. Opposition to what? The opposition to oscillatory motion by resistive or dissipative forces. Because they are dissipative, by definition, what that really means is that they reduce the total energy of the system. They dissipate the energy. Damping causes total energy, and hence the amplitude to decrease. So what does this look like graphically? If we imagine a displacement time graph, damping is seen by a reduction in the amplitude on a graph. So maybe we first go up to that amplitude and down to here, and then next we go to here, then down to here, and then here, then down to here. So the graph goes up and down and back up, then down, then back up, down, like that. And you can see that with each successive oscillation, the amplitude, the amplitude, XO, is getting smaller and smaller. is the characteristic of damping on a graph. Notice, even though the amplitude decreases, the period and frequency thus also do not change with subsequent oscillations. The period does not change with subsequent oscillations. And we can see that on the graph. Here's the period. The next oscillation, right? The next oscillation is this. And it takes the exact same amount of time as the first oscillation took. And the final oscillation on this graph, again, takes the exact same amount of time. The period is still the same. It takes the exact same amount of time as the previous oscillation. So, in fact, the period of oscillation never depends on the amplitude or the initial or maximum displacement. So just because the system isn't going as far with subsequent oscillations doesn't mean that the period will change. The period stays constant as each oscillation follows the next.